Let's apply what we learned about solving equations where the variable is in the exponent from day 1 of section 10.6 to applied problems, either from finance or from chemistry, looking at things growing or decaying exponentially. This is another flipped classroom lesson for Math 101, our last section, section 10.6, the last day, day 2. On these last two, we're going to look at some arithmetic and algebraic applications of exponential functions, exponential equations. So on this first one, we're talking about some money that's been deposited, and we have to assume that there are no withdrawals made. It's going to compound interest on a monthly basis. The formula for this, it'll perhaps look different in some different textbooks, but the textbook I'm currently using has the formula written the following way. The future amount or future value is equal to P times all of the following, where P stands for the principal or present value. It's multiplied all of the following, where R is the rate of interest expressed as a decimal, N is the number of times per year that interest is compounded, and T is the time in years for which it compounds. So in part A, we have how many years? Going back to the original information, $1,500 was put in. We've got an interest rate of 3%, so 0.03 as a decimal. It's compounded monthly, so N is 12. That 12 shows up again up in the exponent, and this is going on for a time T of 5 years. Notice how it's only N down here, where it's N times T up here. It's not just 12 here, and it's not 12 times 5 down here. Now on the TI-30, this could be typed in all at once, but if you did have to break it down, 0.03 divided by 12, add the 1. So we finish the parentheses, and then we're going to raise it to whatever N times T is. Now, if you've got parentheses on your scientific calculator, you put parentheses around the exponent and have it do the multiplication, and then raise that power, raise that previous answer to that power. But 12 times 5 is 60. I want you to notice what we have here so far is something that's between 1 and 2. Very rarely will you get a question where you get something bigger than 2. It takes, what that would mean is if it's 2 or bigger, the money is doubling or more. And it takes a combination of a good interest rate, something higher than 3%, number of times per year that it's compounded, and how much time goes by. The interest rate, the 12 times per year, and the time, these are all pretty low. Now I multiply that by 1,500. Now we're supposed to round that to the hundredths place, 2 places after the decimal point, because except for gas prices, that's what money gets rounded to. So that's going to round to 1742.43. And since the 1,500 was in dollars, so is this. $1,742.43. So that's a gain of almost $250 into 5 years, but you have to start with a good amount of money to begin with. The interest rates, how many times per year, and the number of years, those are all pretty low. Now we have a compound interest question. It is not saying continuous compound interest. It just says compound. Continuous is at every moment of time. This says daily. So M in your formula is going to be 365. You may be using a textbook where it uses little I to stand for the periodic interest rates. That 1.6% is an annual interest rate without taking into account the effectiveness. So I've replaced I with R over M because that's the first thing that I'm going to do by the order of operations anyway. So whether I remember this formula and that I equals R to the M and that N equals M times T, I just put everything in there all at once and follow the order of operations. One formula to remember instead of 3. Okay, so 365 divided into 0.016. Notice again, that 1.6% as a decimal, I have converted that to a percent by moving that decimal point 2 to the left. I'm going to divide that by 365. So let's see what we get there. Now, making sure that the calculator shows me every single decimal place that it can. If you're working with a TI-84 or TI-30, you can go to mode and set it to float. Adding 1 to that. Technically, since this is already showing the most that most of the TI-84s can show, 10 digits here. Technically, when we add 1, you're not going to see that last 4. After the parentheses, I need to raise it to this exponent, but there's work to do with the exponent. 365 times 4 is 1460. By the way, this will apply to many of the questions from here on out. Usually you're going to have something that's between 1 and 2 that is raised to a power. If it's bigger than 2, then you're talking about doubling, tripling your money, things like that. That doesn't happen very quickly. You would have to have a very good interest rate or a long amount of time or some nice mix of the two to start to get things to double and triple. So I found out here what 1.000043 blah, blah, blah to the 1460 is. And finally, I do the multiplication. After rounding, because this is money, to the hundreds place, $551.08. Now notice in this next one that we're asked how long would it take the money to grow to $2,000. That's more than this. It's more than our answer to part B. So this time we've got a value for A. And we don't know what T is. I'd already worked out what 1 plus 0.03 divided by 12 is previously. That was the 1.0025. You don't want to multiply that by the 1500. Because if we knew a number for T, like we did in part A, we would raise what's in the parentheses to the power first. We're going to have to isolate that 1.0025 to the 12t. 1500 is multiplied to it, so divide by 1500. $2,000 over 1500, that's going to reduce to 4/3, dividing top and bottom by 500. So now I'm going to take the natural log of this and of the 4/3. So I can get that exponent with a variable in there out of the exponent by using the power rule for logarithms. Got 12t times some number with the 1.0025 equaling the natural log of 4/3. All in one step, I'm going to divide both sides to get t alone. T is being multiplied by 12 and by the natural log of 1.0025. So I'm going to divide natural log of 4/3 by 12 times the natural log of 1.0025. Now again, with that same principle, interest rate, and number of times per year that it's compounding, it took 5 years to get to the $1,742.43. And now we're going for something higher. So we should expect the number of years we're going to get to be higher than 5 years. By the way, remember that this is supposed to be rounded to the nearest tenth. So here we go with that. Natural log of 4/3 divided by all of the following. So I'm putting parentheses around this multiplication so that it knows both the 12 and the natural log of 1.0025 are in the denominator. Close the parentheses for the log, and for the denominator, expecting an answer bigger than 5. And to the nearest tenth, coming up with 9.6. And that would be in years. Now we want to talk about continuous compound interest. Although interest is being computed at every moment of time, the formula is actually nicer. And so we're putting in 1,225 for the principal or present value, and we are given the rate of interest, annual rate of interest, convert that to a decimal by moving 2 to the left, and we're looking to compute the future value. Whether I call that A or F, it doesn't matter. It's just going to be calculations according to the order of operations, multiplied by the 10 years up in the exponent, raise e to that power, and then multiply by the 1225. And since we're talking about money, without being told otherwise, we're thinking that this is money in the US. So I would round that to the nearest hundredth and come up with $1,535.63. In number 11 here, it looks pretty similar to what's in number 10, except that the principal or present value is lower than what we started with. We should therefore expect the future value to be lower than the future value computed in number 10. I can say that because we're still talking about a time of 10 years and an annual interest rate of 2.26% that was continuously compounding. So I converted the percent to a decimal, multiplied by the 10 years, use that as the power of e, and last multiply it to save any of my rounding until the very end. And I come up with $1,504.29, which is indeed less than what we had here. So on this last one, notice that it says that interest is being compounded continuously. If you were to go from compounding annually, where n was 1, to semi-annually, to quarterly, monthly, you could even go with weekly, or daily. You can keep on breaking that down. Every hour, every minute, every second, every half second, or tenth of a second, whatever. If you were to look at what would happen to $1 in 1 year at 100% interest, which of course is a ridiculous interest rate, but 100% interest rate would have R equals 1. Well, that would give you a hint as to where one way that we see that number E, which is about 2.72, where we'd see that come up. And it's going to show up in the formula for continuous compound interest. It's a much simpler looking formula. If it weren't for R times T being up in the exponent, I'd read that as A equals PERT, for PERT shampoo, if you like. Now here we've got 2,000 as a future value in 10 years, and we need to know how much money is being invested at the beginning. This is 3.5. Just like 3% became 0.03 by moving the decimal 2 to the left. Even when there's a decimal already in there, it has to go 2 to the left. Now, whatever this is, 0.035 times 10, we can simplify that. .35. E is just a number. You don't have to use that approximation that I mentioned earlier, because the calculator has an even more exact. This is not all of it, but it's more exact than saying 2.72. So use the calculator's approximation for that. Raise E to the 0.35 power. And that's just something that's being multiplied to P. Let me do it this way. That number, that's about 1.41906 something, is multiplied to P. So we're going to divide both sides by that number to get P alone. And we have already found out what the denominator is. So I'm going to divide 2,000 by that previous answer. And I'll do the same thing of rounding to 2 places, because we're talking about US money. So that's going to be 1409.38. And that concludes some additional examples of solving equations that have variables in the exponents, or within logarithms, or some application questions. Have a good one. Let me know if you have questions. And for our last question of the review, the last toughest question that the spring class had, we have a formula over here for the decay of a radioactive isotope that looks similar to the continuous compound interest formula with some values plugged in, although we've got a negative exponent here. So part A, time of 10 years, that's being plugged in for t. You're just going to be calculating. You may have a calculator that lets you type this in all at once, but if you don't, exponents would be before multiplying by the 600, which means we'd have to figure out what that number is in the exponent. E to the negative 0.43 power is about 0.6505 090 65050 90947. So multiplying that by 600, I'm getting 390.305 4,568, and we're supposed to round to the nearest hundredth. That 5 in the thousandths place is going to round that up to 390.31, and since this is an amount, the initial amount was in grams, so this will also be in grams. Now, in part B, how long will it take the initial sample to decay to half the original amount? The original amount was 300. In 10 years, it is closer to a quarter, I guess, of the initial amount that is decayed. So I expect this is going to take longer than 10 years. It's worth pointing out that in 1996, oh, never mind. Okay, so half the original amount. So our future, well, final amount. The initial amount is still 600. What's unknown this time is the value of t. And it wouldn't have mattered whether we started with 600 or 800 or 1,000 or 1,562. Your first step would be to isolate part with e to some unknown power by dividing by 600. Solving a question like this would always have the next step being e to that unknown power equaling 1/2. Taking the natural log of both sides, it's going to cancel stuff on the left because it's the same base. By both sides by negative 1/2, sorry, by negative 0.043, that is. Again, you may have a calculator that lets you put this in all at once. If you do, terrific. Otherwise, well, 1/2 is 0.5, so natural log of 0.5, that's a negative number, about 0.69 something, but I'm not going to round it, not yet. But by negative 0.043, I'm coming up with t is approximately 16.11970187. That was also supposed to be rounded to the nearest hundredth. The 9 is going to round that 1 up to a 2. We have approximately 16.12 years is what it would take to have half of the original amount. And that concludes our look at the toughest questions from the spring final. If you have questions, contact me. See what we can do to clear things up. Have a good one.